Have you ever wondered what could happen if a white dwarf star exceeded a certain mass limit? That's where the intriguing concept of the Chandrasekhar limit comes into play. Named after the brilliant astrophysicist Subramanian Chandrasekhar, this limit is the tipping point for the fate of a white dwarf star. In the simplest terms, the Chandrasekhar limit is essentially the maximum mass of a stable white dwarf star. To give you an idea, the currently accepted value of this limit is roughly 1.4 times the mass of our Sun. Go beyond this limit, and the star can no longer maintain its stability. White dwarf stars primarily resist gravitational collapse through a force known as electron degeneracy pressure. This differs from main-sequence stars like our Sun, which resist collapse through thermal pressure. Now you might be wondering, what exactly is this electron degeneracy pressure? It's a quantum mechanical effect that arises from the Pauli exclusion principle. This principle states that no two electrons can be in the exact same state, meaning that electrons must occupy a band of energy levels. When a white dwarf's mass exceeds the Chandrasekhar limit, this pressure in the star's core is no longer sufficient to balance the star's own gravitational pull. So what happens when a white dwarf surpasses this limit? The star becomes subject to further gravitational collapse, evolving into a different type of stellar remnant. This could be a neutron star or even a black hole. However, white dwarfs with masses up to the Chandrasekhar limit remain stable. Now, the discovery of the Chandrasekhar limit was not without controversy. When Chandrasekhar first calculated this limit, the scientific community initially ignored it because it would logically require the existence of black holes, which were considered scientifically impossible at the time. Needless to say, we've come a long way since then in understanding our universe. So, let's recap the key points about the Chandrasekhar limit. It's the maximum mass a white dwarf star can have before it can no longer resist its own gravity. This limit is roughly 1.4 times the mass of our Sun. If a white dwarf does exceed this limit, it can collapse into a neutron star or a black hole. This limit was named after Subramanian Chandrasekhar, who calculated it in 1930, and it was a concept that was initially ignored due to its implications about the existence of black holes. The universe is vast and full of wonders, and it's through understanding concepts like the Chandrasekhar limit that we begin to unlock its secrets.